Rain1290 with you, bringing you another thunderstorm analysis, specifically a severe thunderstorm analysis, since there is a threat, a looming threat for eastern Ontario to southern Quebec and portions of the northeast US. So this will be especially for June 21st and more especially into pre-dawn June 22nd. And these thunderstorms could be widespread in coverage as well. So without wasting any more time, let's see why this threat exists for these regions. Okay, so let's start with an evaluation of our synoptic chart. So this is progged for June 21st in the evening and going into pre-dawn June 22nd. So as you might recall from previous videos, these synoptic charts are designed to show us the location of different pressure areas, of high pressure zones, as shown by these blue H's, and low pressure zones shown by these red L's. So the red L's also contain fronts, like cold fronts or warm fronts. So you have these cold fronts as spiky blue lines, as you can see here, for example, in the western US and up into western Canada. And you can also see these red lines with semicircles on them, red semicircles representing a warm front. Now look off to the northeast, like in upstate New York and eastern Ontario, southern Quebec. And so really what you're seeing here is an extension of this warm front. And this eastern extension, it looks like a cold front, warm front hybrid, but in actuality, that's not the case. It's just a stationary component of this warm front, this elongated warm front. So this is ultimately what's going to be at play for the northeast, a good chunk of the northeast for late tomorrow evening and going into especially pre-dawn June 22nd. Okay, so we determined that we have a stationary warm front. At least this portion of that warm front is stationary, and it is affecting eastern Ontario to southern Quebec and neighboring northeastern portions of the United States. So really what we want to do here is use surface moisture convergence, that's what this map is dedicated to evaluate how much lift is associated with that front, that stationary front. So there's also a shortwave trough, a potent shortwave trough, which I'm going to show momentarily. So let's go forward in time into June 21st. So this is the morning of June 21st. You can see not a whole lot is happening right now in terms of lift, but as we go further, now we're going to late afternoon. This is the early evening, late afternoon, early evening. You're starting to see this area of maximized lift taking place in extreme eastern Ontario into southern Quebec and going off into eastern Ontario and portions of southern Ontario, especially off the Great Lakes here. But let's go even further. This is late evening of June 21st, 11 p.m., but let's go a little bit further and you start noticing even larger amounts of lift maxima starting to appear, coming in from the northwest pretty quickly and venturing down southeast. And especially just north of the island of Montreal, you're starting to see that zone of maximized lift. So this is 2 o'clock in the morning, June 22nd, and then we can go a bit farther. And notice how these areas, these blobs of maximized lift start to really shift southeastward to affect southwest Quebec in particular, and going northeast towards Trois-Rivières and down into upstate New York as well, in portions of Vermont and eastern Ontario. Okay, previously I had mentioned a potent shortwave trough. Now, similarly to surface convergence, moisture convergence, as I showed previously, we can also conduct an evaluation of how much lift is occurring at mid-altitudes, which is approximately the 500 millibar altitude. And it's showing us vertical velocity, measured in microbars per second. So that's not important. What we really want to focus on are colors like these brighter yellows into oranges, into reds, into hues of purple, and even the blues. Those represent maximized zones of lift. So in general, in principle, it's the same functionality as the surface moisture convergence, except at the 500 millibar altitude. So let's go into later June 21st. Right now we're in the afternoon of June 21st. So let's go later into the period, and you're starting to see this zone, this shortwave trough. So as I mentioned, it is a strong, unusually strong shortwave trough that is evacuating southeast very quickly. So going further, notice how quickly it starts. So I'll go back one time step. Let's go further again. Notice how it is sliding very quickly southeast to affect southern Quebec in particular, and moving southeast towards the eastern townships and portions of upstate New York into northern Vermont. So this is progged for 5 o'clock in the morning, June 22nd, and I'd even go back one step into 2 o'clock in the morning previously. So you can see that this zone of lift is starting to join forces with that maximized zone that I showed previously, with that stationary boundary, that stationary warm front that is settled into this region here. Okay, so a good place to start to evaluate or examine how much instability is taking place is through how much moisture is unfolding. So right now we're in the morning of June 21st, and really what we're looking for here are these blues and grays and even purples that are taking place. That represents the highest dew points and therefore the highest humidity. So looking into the morning period, this is 11 o'clock in the morning, and we're not seeing a whole lot in the areas of focus, but actually, I should probably go back a couple of time steps. Okay, so early morning, you're not seeing all that much in Eastern Ontario, Southern Quebec, but let's go further. So I'll go back to where I started. And you start seeing these blues trying to overspread the region of Eastern Ontario, the northeast of the US, and eventually finding its way into Southern Quebec. So this is pretty significant moistening that's taking place here, and it is actually helping to maximize instability to unusually high levels into the overnight period. So this is quite an unusual situation that we're seeing here. So going into the overnight period, so now this is 5 o'clock, June 21st, for example, you're starting to see these purples starting to overspread the region. These are dew points of 70 Fahrenheit or greater, so approximately 21 Celsius or more. 21 to 23 Celsius. But even if you go eastward into Eastern Ontario, so you're getting similar dew points around 20 Celsius, which is about 68 Fahrenheit. And that is taking place overnight. So we have some rapid humidification taking place overnight. And I think this is going to serve as a means to really amplify instability during these hours. Okay, so turning our attention to mid-level lapse rates. So notice I didn't include any kind of analysis for low-level lapse rates because this is mostly a late evening overnight period. But the low-level lapse rates that would steepen because of afternoon sunshine the day before will help to have some contribution to maximizing the instability even into the overnight period. Not a huge contribution, but still something. But let's focus on mid-level lapse rates. So here we're seeing these rates of approximately 6 to 7 Celsius per kilometer. So this is a way of gauging how quickly temperatures are cooling with increasing altitude. So right now we're in the morning of June 21st. So I'm just going to extend this animation to include later June 21st and going to June 22nd. And we're seeing these unusually steep mid-level lapse rates overspreading Eastern Ontario to Southern Quebec and much of the Northeast during the pre-dawn period. So this is unusual to see in the Northeast, but at the same time, it is helping to contribute to really helping instability explode during these hours, despite the lack of sunshine. So this is quite something to see. So we're seeing rates as much as almost 8 Celsius. Yeah, pretty much 8 Celsius in some locations, but typically 6.5 to 8 Celsius. And also grabbing Southern Quebec, just barely going later into the overnight period. So this is combining with that low-level moistening that I showed previously, and it will help to maximize instability. Okay, and now just to gauge an overall framework of instability, and as I mentioned in previous videos, the best way to do that is by looking at CAPE, which is a metric of instability, and CAPE stands for convective available potential energy. So the brighter the colors, the more instability that is present. So these purples, for example, show us instability levels or CAPE levels of about 500 joules per kilogram. The blues getting us closer to 1500 joules per kilogram. But let's go farther. This is June 20th, but let's go into later June 21st, and you start seeing how these areas, these regions of really high instability, unusually high instability for these hours, late evening, pre-dawn hours, are starting to overspread Eastern Ontario to Southern Quebec and the Northeast. So you're seeing these values of as much as almost 5,000 joules per kilogram in Eastern Ontario, and even as much as almost 2,500 or a little over 2,500 in Southern Quebec, around the island of Montreal. This is for 5 in the morning on June 22nd. So this is really representative of the steepening mid-level lapse rates plus that aggressive moistening that's taking place. Huge amounts of humidification taking place in these regions. Okay, so putting everything together into what we call a skew T log P diagram. So this is a handy and very intuitive diagram that puts together everything we pretty much looked at and examined. So it's showing us various things here. So as you might remember from previous videos, forecast videos, so the green curve shows us how moisture is changing from the surface. So the surface is about there at 1,000 millibars. And this is the dew point temperature as represented by humidity. So it shows us how that dew point or how that moisture is changing with increasing altitude all the way up to roughly the tropopause and going beyond. The red curve shows us the environmental temperature with increasing altitude, and this dashed blue curve shows us a parcel temperature. You can ignore the light blue curve for now. So that's pretty much what this is showing us. And now on the far right, this is showing us wind speed and direction, represented by these wind barbs, starting from the surface, again 1000 millibars, and working our way up to the tropopause and beyond. So really what it's showing us is how wind is changing in behavior in terms of speed and direction. And you can see a pretty sizable shift in wind direction with increasing altitude and a good increase in wind speed, which makes sense because we know that warm air advection is occurring, and that's why you're seeing this orientation within the boundary layer. And for those of you who don't know what the boundary layer is, that's pretty much the lowest 150 millibars of the troposphere, which extends from where we are at approximately 1000 millibars and going beyond to about 850 millibars. So essentially 1.5 kilometers above the surface, or also known as 1 mile above the surface, approximately. Now, really what I'd like to show you is how this behavior, this temperature behavior, and also the wind speed and direction behavior is changing over time ahead of that stationary warm front that we looked at the beginning of this video. So this is shown for 11 p.m. This is a sounding profile taken around the Montreal area for late in the evening of June 21st, around 11 p.m. Now let's go 3 hours later. Okay, and on top of these more defined wind shear profiles from the surface going up, we actually see some very strong 500 millibar wind speeds as represented by this flag-looking icon and the little wind barb there. So when you see these flags, it represents very strong winds at certain altitudes, and that's what's taking place at the 500 millibar altitude. Also, drawing your attention to the amount of instability that's growing at 2 o'clock in the morning, or around 2 o'clock in the morning. This is consistent with the amount of moistening and the steep mid-level lapse rates. That's what's being shown here, approximately 7 to 8 kilometers Celsius per kilometer, taking place at this range of altitudes here. At this point, we're getting a dew point of 64 Fahrenheit. So this is a sharp increase from earlier in the day on June 21st. This is a pretty good jump into the pre-dawn period. Okay, so now watch how this area of Cape also intensifies when we start going deeper into the overnight period, or pre-dawn. So as I mentioned in previous videos, I won't go into extensive detail about this, but the Cape region, when you're reading a skew-T log-P diagram, what you're looking for are these gaps between this blue dashed line. As I mentioned before, this represents the parcel temperature, and this red curve represents the environmental temperature. So when this blue dash curve is to the right of this red curve, we know that it's cooling at a slower rate, which means it's warmer than the environmental temperature. And what this does, it creates instability because that parcel temperature is more buoyant and is able to rise more freely. Okay, so moving into 5 o'clock in the morning Eastern time, so still around the Montreal area. All of these are taken as sample points from the island of Montreal. Okay, so watch how the amount of Cape, it really boosts for the overnight period. So we actually see a deeper distribution of Cape as well. And also you're seeing some drying taking place. See, this dew point temperature is actually steepening pretty quickly. So the air is actually drying as well, and this can actually help to fuel stronger downbursts in thunderstorms. Spectacular, I guess, is probably the right word for this. As you can see how this shearing profile is really magnified. So there's some really strong wind shear profiles taking place here. First from the southwest near the surface and going all the way up to about 500 millibars where they become more westerly. So we have a very strong wind shear profile taking place here, suggesting very organized convection and fast-moving thunderstorms altogether, and very quick thunderstorm consolidations. So you have aggressive thunderstorm mergers into multicellular families. And at the same time, notice our 500 millibar temperatures, not particularly cold. I mean, we're at approximately -8 or so, but this is still enough to fuel some hail production, small hail, granted, in some of the most organized thunderstorm families. This is cold enough to support frequent or intense lightning with some of these thunderstorms, in addition to the amount of humidity that has now developed at the surface. We are now in very high humidity standards at around 69 Fahrenheit at 5 o'clock in the morning around the Montreal area. So this could help to further contribute to the idea of more rigorous lightning frequency, including high energy strikes. Okay, so just providing a bit more intuition as to where I think thunderstorms will initiate and how they're going to migrate. In general, we know our stationary front is located somewhere here, and the warm front itself is over this way. But the stationary portion of that warm front is lying right around this section of eastern Ontario into upstate New York. So we expect the most favorable lift around this zone and a little bit northeast of there around this area. So thunderstorms in general will be allowed to move in a sort of curved manner, moving in a little bit in this fashion along that boundary and going there as well, like more or less in this kind of direction. So sort of curved along this boundary, in and along this boundary, and also just south of that boundary as well into eastern Ontario, like this, and a large portion of upstate New York and into Vermont, and I would even go a bit farther this way as well. Because keep in mind, we also have that shortwave trough that's joining forces with this boundary. So this will amplify lift and taking advantage of that increased instability in this area. So ultimately, I do expect thunderstorms to be moving in larger groups, so large families of multi-cell thunderstorms that are able to move in this direction. Now, I also mentioned the directional component. I actually stressed a lot on this back in the sounding profile section of this video. So we could have several thunderstorms, rotating thunderstorms, as part of these families as they move to the southeast. So this area in particular could see several rotating thunderstorms during the night. So this could actually feature a situation where we have these nocturnal, weak, isolated tornadoes in this zone in particular, where lift and instability are especially high. Now, I would expect them notably in eastern Ontario, where instability is especially high, because as you might remember, the steepest mid-level lapse rates are actually unfolding in this region over here. So these thunderstorms that are moving into Eastern Ontario, I think will have the best chance to rotate and ultimately produce an isolated tornado during the pre-dawn period, which is a rare situation, to see tornadoes overnight in this region of the, in the Northeast in general, and Eastern Ontario, Southern Quebec. But I would also include that risk towards southern, southwest Quebec, since there is sizable directional shear in this area as well, and strong organization. Now, in general, these thunderstorms will be mostly capable of strong straight line winds, so I do expect some damaging winds, straight line winds with many of these thunderstorms, so I think that'll be the primary hazard. And as I mentioned, many of these thunderstorms will be capable of intense lightning altogether. Some of these will still be capable of small hail further. And of course, there'll be a local flooding threat because there's so many of these thunderstorms that are forming in families that repeatedly struck areas will have the best chance for local flooding. So that flooding hazard will be there as well. If you made it this far, I really, really appreciate it. I know it's a lengthier video. It's a lot to absorb, but I think it's necessary at the same time to be able to put out these hazards and just make you aware of the situation tomorrow, late evening into especially the overnight period. So we'll see what happens. I'll have some updates below this video in the comment section if necessary, in tandem with the newest data that is released. Again, if you find this useful, I encourage you to subscribe to not miss out on upcoming videos and outlooks like this for other thunderstorm situations and outlooks in general. And in the meantime, I'll leave you with these videos if you're interested in thunderstorm footage from the Montreal area and in Orlando, Florida.